What's up everybody, welcome back to Basic Chem 101 with Sihlebonani. My name is Sihlebonani and today we'll be dealing with the Aufbau Principle. Moving on from the last lesson that we did in the last video. If you didn't check that video, go check it out, then come back to this one so that we can move on together. Please don't forget to subscribe, don't forget to share this video. You can also comment if you have something to say. But now, let's get to it.
Let's go. This is how every child that wants to make it one day. Simple say class and presence of mind is elsewhere. Swing out with Suzanne, I've not moved that day. Already Alice funny and the timer is nowhere. I know your pain, you don't have to be scared. The gems are very pure, they the written and focus. Keep that pen and paper, they will take you to that day. In the meantime, stand up, help me.
So we're doing the building up principle or the Aufbau principle. But let's start with what do we know so far. We know that there are 4 quantum numbers. We also know that quantum number n, which is the principal, you have quantum number L, which is your angular momentum. So you know when n is equal to 1, you know your L is equal to 0. Also when your L is equal to 0, you know when you have 0, you have the s orbital. When n is equal to 2, L is equal to 0 and 1. When L is 0, you have s orbital. When L is 1, you have the p orbital. When n is equal to 3, L is equal to 0 or 1 or 2. 0 is equal to s, 1 is equal to p, and 2 is equal to d. And when n is equal to 4, L is equal to 0, 1, 2, 3. 0 is s, 1 is p, 2 is d, and 3 is f. So you know that in these subshells, the s subshell can contain 2 electrons, the p subshell can contain a maximum of 6 electrons, the d subshell can contain a maximum of 10 electrons, and the f subshell can contain a maximum of 14 electrons. So, and we also said if you have an atom which has 3 electrons, for an example, you have lithium, you can do what is called your electron configuration, or you can draw what is called your orbital diagrams to show the distribution of those electrons in a particular atom. So if you have 3 electrons, you know that you have in the first shell, you have 1s, which is 2 electrons. Then in the second shell, you have 2s, which is 1 electron. And then if you have 10 electrons, an example would be neon. In the first shell, you have 1s, a maximum of 2 electrons. And then in the second shell, you have 2s and 2p, which is 6. So you'll have 10 electrons. That is your electron configuration. Also, you'd have, if this is 1s, you'd have, if you are looking for orbital diagram, you'd have something of this nature. And then here, you have 1s, which is 2 electrons. Then you have 2s, which is 2 electrons. Then you have 2p, which is 6 electrons. And then the direction of your electrons will be based on your spin quantum number or your Pauli's exclusion principle. This is what we know so far. Now, what is it that we want to know? So let's say you have 5 electrons and then you want to do an electron configuration, or you want to do your orbital diagram. So based on what we know, we can say if this is 5 electrons, which means I'll have 1s, 2s, and 2p. So can have this 1, 2, 3, 4, 5. Then I have 5 electrons. So what I want to know is how do I, or what is the guide for me to be able to fill these electrons in a correct manner. So that is what I'm looking for. And something that will help me get to that answer is what is called your Aufbau Principle, or your building up principle. So let's look at electron configuration and say there are different possible ways of writing electron configurations, and one of them would be writing your electron configuration in a ground state, or writing your electron configuration in an excited state. So atoms, when they have electrons, they have energies that are there. As we have said, if you look at your principal quantum number, your n is equal to 1, has the lowest energy compared to n is equal to 2. So when an atom on its own is at the lowest energy level, it is said to be in a ground state. And we'll be focusing mostly on the ground state to try and explain this following principle. And that's because the ground state on its own, it helps us in knowing chemical properties of most atoms. So the building up principle, it guides us in writing the electron configurations in a specific order. So what it actually says is that you first have to fill the orbitals or the shells in the lowest energy level, and then you move up to the next energy level. For an example, if you have 3 electrons, like we've been saying, what you will fill up first is the 1s. 1s is the lowest energy level. So you'll put your 2 electrons in the 1s first, and then you move on to 2s, then you have 1 there. So the building up principle, it gives you that order. And then from the 2s you move to the p orbital, and then from the p orbital you move to the d orbital. But as you move one shell to another, you find that, let's say in this case, when you have 10 electrons, you'd have something of this nature. Then you move to 2s, 2, then you move to 2p, 6. And then when you have 11 electrons, it's going to be 10, and then if it's 11 electrons, you're going to move to 3s, 1. Then there's 3p, there's 3d. As you add electrons, you'll have to move. But you will find out that there are some changes, because what you will expect is that you go from S to P to D to F, and then S, P, D, F, as you go up to those higher energy levels. But the building up principle, they say that the more your atom becomes bigger, or the more energy levels that you are filling up, the s orbital of a higher shell and a d orbital of a lower shell, they become very close in energy, such that you would first have to fill up the s orbital of the higher shell compared to the d orbital. But you don't really have to talk a lot about those technicalities or those specifications, because there is a way of you knowing how you can actually, or what is the route that you can take in filling up your electrons according to the building up principle, which is why we have these subshells here. So the Aufbau Principle will follow a certain order which goes in this direction. So you'd fill first the 1s orbital, and then it turns here, then you fill second the 2s orbital, then it goes like this. You fill the 2p, 3s. This is still the order that we expect. And 3p, then 4s. After 4s, 3d. So if you can be able to make this type of a diagram, and then you can be able to use it for you to be able to make what is called your electron configuration in a ground state according to the building up principle. So you will have to do like this: 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, in that order. So this is how you would fill your electrons. So let's look at some few examples in trying to explain the building up principle. So we spoke of lithium. Let's now look at hydrogen. We know hydrogen has 1 electron. So hydrogen only has 1 electron. So the electron configuration for hydrogen is 1s1. Then if you look at helium, helium would be 1s2. And then all the orbitals for helium are filled. So if this is helium, so the 1s can only accommodate a maximum of 2 electrons. And helium has n is equal to 1. So it only has 1 shell, meaning you only have the s orbital. So when you have the s orbital, you have the maximum number, which is 2, which means helium is unreactive. So because all the orbitals in helium are filled, so that's why you'd find helium in what is called your noble gases, or in your group 8, because in the noble gases, all the orbitals that are available for electrons to be filled there, they are filled, so they don't need other electrons. But for hydrogen, which has only 1 electron, it means this one is reactive because you can add another electron on the 1s orbital or 1s subshell. So because this one is unreactive, if you look at lithium, lithium has 3 electrons. So lithium has 3 electrons. So this will be 1s2 and then 2s1. So if you look at this part, which is this one is the same as helium. So we can also rewrite this as a noble gas configuration of lithium, which is helium. We know that helium is filled, so this part is helium. Then you have 2s1. And then if you look at beryllium, you would have 1s2, and then you have 2s2. This one is lithium, this one is beryllium. So we can write this as helium 2s2 if we're looking at a noble gas configuration for beryllium. Beryllium has 4 electrons. But you can't say that beryllium is now noble when you are looking at this, because you know that in the second shell you also have the p orbitals, which is in beryllium, they have not been filled yet. So the reaction in beryllium will be taking place in the p orbitals. So this one is still reactive. But if you look at neon, you know that neon has 10 electrons. So you have 1s, 2, then you have 2s, 2, and 2p, 6. All the orbitals here are filled because you don't have anything after 2p. So neon also is unreactive, and also it is a noble gas. So if you look at now, you have sodium. Sodium is 11 electrons. So for sodium you have 1s, 2, 2s, 2, 2p, 6, and 3s1. And then this part is the same as neon. So the noble gas configuration for sodium would be neon, then 3s1. So you do almost the same thing. So if I'm looking at potassium, the noble gas configuration for potassium, I know that argon will be the noble gas that takes the core electrons, and then I have 1, 2, 3, 4, and then I have 4s1. If I'm looking at potassium has 19 electrons. So argon has 18 electrons, and then all the orbitals are filled for argon. And then you have 4s1. So if you can keep practicing doing your entire electron configuration, and then you do your noble gas configuration, you find that for your group 1, everything will end with your noble gas, let's say your noble gas, and then S1. Then for your group 2, it's S2. And then you will find out that if you're looking at the main group elements, in group 1 and group 2, the s orbital in group 1 and 2, the s orbital is filled. And then if you look at group 3 up to group 7, you find out that from group 3 to group 7, you find out that the p orbital is filled or is being filled. And then in the transition element, which is transition metals, you find out the d orbital is being filled. And in the inner transition metals, you find out that the f orbital is being filled. So this side is your s block, and then that side will be your p block, and then your transition will be your d block, and then your inner transition metals will be called your f block. So this you will all know because you understand the building up principle. Then, but there are only a few exceptions to the Aufbau principle. Let's talk about it. So if you look at chromium has 24 electrons. So if you do your electron configuration, you would do something of this nature, which is your argon. So you will write this as argon, and then you have 4s2, and then you have 3d4. And we can also look at copper. So if we look at copper, you would say your core is argon, and then you have 4s2 and 3d9. But in actual fact, this one would be argon, 4s1 and 3d10. So these would be your exceptions. The exception is that when you are filling the d orbital, there's a rule that say it's either you half fill the d orbitals first, or you fully fill them before you fill up the s orbital. So in this case you had 4, so the closest would be for you to fill this one to be 5, which is half filling, and then you take 1 from here, you put 5 there. Now when you have 9, you can take 1 here to make it 10. So when your d orbital is 4 or your d orbital is 9, you can take from the s orbital to half fill or to fully fill the d orbital. So that is those are the exceptions to the building up principle. So if you look at what we've been doing, we've been having the entire electron configuration, and if you know the noble gas configurations, you can do the noble gas configuration for each atoms, and then for each and every atom, these electrons outside the core or the noble gas configuration, these electrons, you call them your valence electrons. So these are the electrons outside the core electrons, or the electrons that are fully filled. You call them your valence electrons. And your valence electrons are the ones that take part in chemical reactions. And if you look at group 1, all the group 1 elements have 1 valence electron. For group 2, you have 2 valence electron. For group 3, you have 3 valence electron. And then these valence electrons are the same for group 1 has the same number of valence electron. Group 2 has the same number of valence electron. Because of these same numbers of valence electron, you will find that atoms or elements in one group have similar chemical properties because the electrons that take part in a reaction are the same or are the same number. So your building up principle gives you an idea of where to put your electron or your atom in your periodic table, or look at the properties. And that is it for today. Thank you very much for watching, and please don't forget to subscribe. Please don't forget to share the video. This has been Basic Chem 101 with Sihlebonan. My name is Sihlebonan. I will see you on the next video. This is the GeltonNation.